So I'm a postdoc at the University of Montreal and associated with CIFAR. Besides that. So let me maybe first take this as an opportunity to tell you about the current state of the art about like generative modeling and how it relates to supervised learning. So we all know the success story for supervised learning in deep learning, where typically you are given a data set, a huge data set hopefully, and you're given some targets that are typically very low dimensional. So low dimensional both relative to your input data and low dimensional relative to the number of data sets you actually have available. And so we know the success story. You can build systems that have lots of parameters, and then you adopt these parameters, and in the end you have a machine that can kind of, with a high success rate, predict the targets that you wanted to see. There are some other problems that we don't see applied so much yet. And these problems often relate to applications where you want to generate complex data, where you want to generate high-dimensional output data. And so if you think, for example, predicting a single category from an image, that's high-dimensional input, some million pixels, and the output is essentially one dimension. It's like what's the category of this. If you have some kind of language model, this is essentially also very low dimensional. If you think about each word in a sentence as one dimension, then you typically have outputs that are maybe 10, 20 dimensional outputs. And so we have seen a lot of progress on this. But we are not there yet to generate really high dimensional output. And with that I mean, for example, generating complete images. Or taking the inverse problem of what we have seen today, what we have seen yesterday, of taking an image and translating it into a sentence. It would also be pretty awesome to go from a sentence to an image. It would be nice to have language models that don't just generate a single sentence, but that generate actually a whole paragraph of consistent text that makes sense, or a full chapter, or maybe a book. So these are some kind of problems that are interesting, but generative and unsupervised learning, of course, also relates to this pretent training stories that were iterated some years ago, that you could, if you don't have enough labels, but you have a lot of input data, then you could pre-train an unsupervised model and then transfer the weights to a supervised system. I don't think this is the best way to deal with in these situations, but that's another story why unsupervised learning is probably very interesting. Just to give you a glimpse of the state of the art in generating images from these models. So at the top there you see a model by Emily Dalton. So that was very recently published, where you can kind of see images that were generated by a model that was trained on natural images. And obviously this has kind of the correct structure, but it's far away from from the success story we've seen for supervised learning. At the bottom we also see samples from some variational autoencoders, and there are more models that kind of play in this direction. So let me maybe, for comparison, I think this makes an interesting data point. You probably have all seen these images from a deep dream model. I'm not sure if everybody knows how these were generated. So the procedure behind these images is basically that you train a normal supervised convolutional network, so as we kind of have seen multiple times today. And then you take the trained model that were trained, including the labels, and you kind of run it backwards. So you change the input such that the model is more happy with the input image. And as a result, you get these images that kind of don't look really realistic or natural to most of us, but that still show that these supervised models that were trained to predict categories, that these models learned something about the input data, that these models learned the structure of what images look like. And I think that's an important story, kind of one important point to take away from this, from these images. And that is, so this was a model that was trained to predict categories, and yet it was able to you can misuse it to generate these kind of fine-grained, high-frequency structures in images. While at the same time, we have supervised models that are created to model input data, and yet, in a certain sense, they are not much better than what we see here. So I think the takeaway message from this is that we still have something to learn about how to perform unsupervised learning, how to actually train models to do that. Okay, so how do you go about unsupervised learning, generative learning, with modern deep learning kind of methods, or what we know about deep learning nowadays? So I think there are about three main aspects that make deep learning so successful and that play an important role. And that's on the one hand side that you use multiple layers of abstraction. So whenever you want to transform something, you use multiple layers of abstraction that capture different aspects and different hierarchies of information. Then there's, of course, distributed representation. So we have lots of units in each layer. And also very important that we use large models that have huge capacity, that can adopt, and that are easy to train with standard methods like stochastic gradient descent. So what can we do? How can we leverage this to get generative models? And one kind of obvious way is that you start with some simple random distribution at the top. So for example, simple Gaussian noise. So it's just a noise source, Gaussian noise, or independent bits, just Bernoulli variables. And then you use one of these multi-layer networks to transform this noise into the data that we actually want to see. So this transformation could be a convolutional net run in the other direction. You could take a more classical view and not just think about your source of randomness at the top level, but you could also think about having multiple layers of random variables that then in the end go to your data that you want to generate. This is actually well known, and this is a directed generative model. So there's a lot of literature about that. That's a well-known kind of approach to generative modeling. There's also a belief net and a Bayesian net. So these terms in this context here all refer to the same thing. Multiple layers of variables that might depend on each other and that start with a simple independent Gaussian noise, and then you go slowly towards your data that you actually want to generate. But thinking about this problem in this way makes it kind of obvious where the problem lies. That is, while it's easy to go from the noise to your data, it's a hard problem to do inference. And to train these models, we actually want to adopt all these knobs and all these parameters to generate the data that we want to see. But to train this model, we need to go the other direction. We need to present an image to this model, and then we need to go upwards. So what's the high probability state of all these latent variables? And then we could train the model to generate better images. But we know that this is in principle intractable. There's a huge literature how to do that, but there's no simple way to do it. But what we could do is we take a second neural network. So we now have two neural networks, each having its own set of parameters. There's one network that runs from the input data up to some latent representation, some latent configuration. And there's the generative network that runs from this latent representation, from some noise, down to the actual image that we want to see, or data that we want to see. And our task here is now to train both of these models jointly. So the standard way of doing that is that you consider the generative network, typically we call it a P, to be kind of the authoritative network that we want to train. We want to make this model as good as possible, and at the same time, we want to maintain this auxiliary network, the inference network, approximate inference network, to do kind of inference for us whenever we train the model and whenever we want to demonstrate, give some input data. So it turns out I've been playing with these kinds of models for quite some while, and turns out, so these produce the samples that I showed you in the beginning, and I think we can clearly do better. it's not yet clear what is the best way to move forward. But one thing I noticed was that when you make this inference network more powerful, if you kind of add capacity to the network, or if you make it autoregressive, so if you enhance the expressiveness of the inference networks, that you can get much better results, although the generative network is still the same. So I think this indicates that there's a mismatch between the capacity or between the powerfulness of the generative network and the inference network. And one idea I wanted to tell you today was how this can be kind of symmetrized to make these two models both actually approximate inference models for a third model that we want to train. And the basic idea is actually pretty simple. So if it is true that the generative model and the inference model kind of don't fit because they can model only different kind of complexities, we could define a new model which is basically the mean between those two models. So we have the P model that runs from the data upwards, we have the Q model that runs upwards, we have the P model that runs downwards, but we can now define a model P star that's actually the mix, the geometric mean of these two models. And then we consider suddenly both the P and the Q only approximations to this true model that we want to fit. And that should ensure that we don't get this mismatch between generative model and inference model. And actually, I will skip most of the math. I had prepared 2 slides of math. So there's a bit of algebra, a bit of math that tells us, that actually makes sure that we can show that these two models, P and Q, will align and that they will get closer to the generative model P star that I just mentioned. But also my time runs out. Let me quickly just show a few preliminary examples of this. So what you see on the left-hand side, the A, are samples that are, in this particular example, generated from the top-down model P. And if we correctly adjust our sampling procedure such that the capacity of the model P comes into account, we can kind of see that the samples are cleaned up to better model, to take the complexity of Q into account. We can run the same model also as an in-painting task, which I mentioned earlier might be interesting. So all the left columns in each block show the ground truth digit that was in the test set. Then we would kind of blank out half of the digit and present the trained model this corrupted image. And the task of the model would be to reconstruct the missing part, the gray part. Yes. And here we have similar results for face images. In this case, A is the block where you just see samples from the model. So this is what the model thinks faces look like. And in the section B, we see kind of in-painting results from these kinds of models. So I think I mostly wanted to demonstrate that there's still a long way to go. So with generative modeling, we are not quite there yet, and we don't have a success story that's comparable to supervised learning. But I think there are lots of applications and lots of things to learn when we get these models running and get them to a similar state as we have seen with supervised learning. Thank you.